Now this is the lesson. We're talking about criteria C requirement. As I said, I made this Google Doc stating what you need to do to get a 7 and 8. You can find this document in the website underneath the sidebar here, criteria C requirement. Now, I'm going to go over this each part individually so that you know what I'm expecting. Now, to get a 7 and 8, you need to, now the B is from the guide. Here's what I write here's what I personally want an explanation. So, collect, organize, transform, present data in numerical and visual form. So what you will need to do is this: A, clear and organize raw and process data table. I want you guys to separate them. Independent variable, first column, dependent variable, second column. Now, second, table should have a title and be numbered. Okay, titled and numbered. So I'm going to give you an example. Now it's on the board too, but I will make it a little bit clear. So let's just say, for example, in the list of experiments and materials I gave you, it is a different concentration of acid, HCl, and let's just say the design I gave you was, this person gonna see how long it takes for the magnesium strip to disappear. Okay, so let's just imagine if that's the scenario. So now you can't just put, say, raw data table anymore. I don't want you to do that. So for your title, you probably will write something like this: time taken for magnesium strip to disappear. It's not the best one, but that's one thing I thought of right now. To disappear. Wow, it's not the most focused. We'll focus this a little bit better. Time taken for magnesium strip to disappear in different concentration of HCl. Okay. So your title need to be descriptive. I should be able to look at your title and know exactly what this data table is about. Okay, and it should be numbered, which means you'll have to say table 1. Okay, so the next table you will be table 2, something like that. Now, in terms of the whole headings need to be clear and units and level of uncertainty, I have also I've also put on the website a lab report format guide. The lab report format guide, as I said, is something I used to give to my other students from other class. But I want you to look at the following format. So here, now this is a bad example, but this is actually the format you should have. Title for each one, the units and level of uncertainty on the second, right below it. The first row is independent variable. All the decimal places are the same. Okay? So in this case, using our current example right now, if you're reading this, it's like, oh, time taken for magnesium strip to disappear in different concentration of HCl. So in this case, your concentration will probably be your independent variable and molar, and then let's just say plus or minus 0.1 molar. And then you have things like O2, O4, O6, O8, 1.0. I'm making something up right now, but that's how I'm making something up right now in terms of numbers, but I want you to focus on how the table is formatted. Then you have here, because you're talking about time taken, right? So you have time, in this case, seconds, and then what did I say the level of uncertainty for seconds? No, for time. If it is something that you have to press the stopwatch. What's the level of uncertainty if it is you're measuring time from pressing pressing a stopwatch?
0.1.
0.1. Thank you. 0.1. And then you have trial 1, trial 2. Where's Jun Sung? Bathroom. Trial 3. Okay. And then you just record your data. Now keep in mind, all your data needs to have the same number of decimal places. So let's just say if you have 6.8 here and next one here is 7 point or 7.0, please do not just write 7, 7.0. All of them should be the same decimal place. Okay? So the lab guy here have this really nice diagram. Make sure you follow that. This format will be good for you even down the road next year and next 2 years. Good? So, headings, titles, sample calculation should be shown for each calculation. Now, I think, Sarah, is it you who asked the question? Okay, so what do you mean by sample calculation should be shown for each calculations? So here, I'm just gonna make up some numbers right now. 7.2, 6.6, 7.5, 6.7. Let's just say there's more numbers. Okay. Sorry, supposed to switch here. So let's just say there are more numbers down here. When you do the sample calculation, you do not need to show work for every single one. Let's just say you want to find the average, right? Average time. You don't need to do one for every single one. Show work for every single one. You just show, it's like, oh, so sample calculation. So you can just say for 0.2 mole concentration, and then you just show the formula average equals 1 plus 2 plus 3, and then you just show that work just for this set of values. You do not need to show the same work for the other stuff. Does it make sense?
1, 2, and 3.
Of concentration 0.2.
Every trial.
Yeah, for every trial for that concentration. Yeah, for that particular variation of independent variable. Okay? You need to do that. Questions? So make sure you show your work, make sure you show your formulas. Process data should be transformed into an appropriate form of graph. Now here's a list of things you need to have for a graph. I'll say it now. If it is a continuous data, then you make sure you use broken line graph. Bar graphs are only really good for discontinued data. Okay, what are people's favorite color? That kind of thing. That kind of stuff. It's not continuous data. Because if you use the wrong form of graph, a few people have learned last time, they lose a law mark in this section. Now, because for this particular criteria C summative, I want you to do it on paper and pencil. You will not need to do you will need to do line of best fit. You don't need to show equation. Okay, so you need to do line of best fit still, but you don't need to do equation. I will want you to graph. Make sure when you graph with pencil. Okay, I want you to do your graph in pencil. Yes.
Will we have graph paper for the...
Will you have graph paper? You will have grid papers. Same kind of stuff that Ms. Kunrad will give. Maybe not as nice, but it's still good enough. I checked it. Okay? So you'll graph with pencil. Make sure you do that. Make sure you follow and have the list of these things. Now, simple error bars when appropriate. In the last summative, I did not ask for simple error bar. error bars are essentially a way to show how spread out your data are. So in this case, your data can be really spread out or very narrow, because usually when you plot this, let's just imagine this right now. You're going to calculate the average. So I'm going to take out my calculator. 7.2 plus 6.8 plus 6.6 divided by 3 gives me 6.866 repeated. Okay, so let's just say it's 6.87. So I'm gonna just plot 1 point. So here, I guess, so for this graph, concentration is down here. So let's just say this is 0.2. When you plot this 1 point, you only plot this point here, 6.87. So let's just say here is 6.87. 6.87. But the error bar that I want you to show is a very simple one, simply because Mr. Tilley and I went to check with both Mr. A, the physics DP teacher, as well as the chemistry teacher. I, being the biology teacher, I know what biology expected. Every single branch of science next year will require a different error bar. Because of that, we are just going to use the easiest one to do. Look up here. So you will just plot the range. So you only plot the range. So essentially here, for 0.2, your range of data is 6.6 and 7.2. So you will just say, oh, 6.6, 7.2 is here. So that's your range of data. Do you guys follow so far? That's your error bar. So it shows how spread out your data are. So all your data are within here, these numbers. Error bars are important because scientists later on, when they compare data, they want to see how spread out your data are. Two things. A, let's just say if you have 0.2 like this and 0.4 like this. Let's just say the average is up here, but your data is spread out like this. Do you think there's a big difference? Do you think there's a difference between 0.2 and 0.4? If 0.4, the error bar look like this, 0.2, the error bar look like this? Not really. Simply because it shows 0.4, your numbers are all spread all over the place. Some of them include what you would have here. Yes, the average is here, but it's all spread out. So it helps scientists to do analysis later on. As well as it shows maybe your experimental design, there's something off, something wrong with that. Why would what's happened here at 0.4 trial? All the trials 0.4. What happened? Why is it all spread out like this? Does it make sense? So in this case, you need to be able to do some form of error bar. And since next year you'll have all sorts of possibilities, we'll pick the simplest one. You just need to plot range. Use range as error bar. Good so far? Yes.
Will this video be on your website?
This video will be on my website, yes. But my personal interaction with you definitely will not. Okay, so make sure if you don't understand something or you have something cross with your mind, make sure you ask me right now or use that Google form until 4 p.m. tomorrow. As I said, I have a very early bedtime nowadays. So, questions? Now, normally we want you to use Logger Pro and spreadsheets like Excel or Google Sheet, not numbers. But because this is a paper and pen one, of course, you just do paper and pen. You have graph paper to make your graph. Make sure you do your graph neatly and nicely. I'll talk with Ms. Kunrad. Manually, yes, by hand. Okay, I'll talk with your math teacher to see what they expect in your math class, and I'll expect the same kind of deal. Questions? Yes.
Then we are also writing the data table.
Um, of course. Yes.
Do you need to write down the data table and the graphs on the separate paper or just on the same?
Preferably on separate paper, since I will only give one graph paper per person. So on the line papers I give you, you make your data table, and then you plot your graph on your graph paper. Just to remind you guys, and I'm sure you have learned this elsewhere, since you're doing a line of best fit, it's better. Since you're doing line of best fit manually, it's better that you use as much of the graph paper as possible because you will have a much more accurate line of best fit. You guys learned this before, I'm pretty sure. Okay? Any questions on this strand? No? Okay. Also, what you need to be able to do is accurately interpret data and explain results using correct scientific reasoning. Now, when you do that, you should look at your graph, describe patterns and trends from the graph using the line of best fit, give detailed account and reasons for cause for the trend. So, let's just say this is your line and your graph looked like this for some reason. I'm making stuff up, okay? So in this case, you will need to give detailed accounts. When I'm saying detailed account, I'm not saying use one line or two to describe this graph, okay? What you smart people, what you will do is that you'll pick, if a graph like this, you probably pick 3 different spots or 2 different spots. In the beginning, in the middle, at the end. So you say, oh, in the beginning of the graph, how's this line? Oh, it's going up really quickly. And then in the middle part, it is slowing down. And then at the end, it is gradually level off if it is a graph like this. If a graph is doing something else, then make sure you describe the graph appropriately. Also, when you're doing 3 separate sections, make sure you pick a point on the line. Okay, pick a point on the line to describe what happens. Okay, so for example, in the beginning, in this point 0.08, the time is this. Okay, this is what we expect you to be able to do this year and next. Okay, so please follow that. So break down your line of best fit into three parts. Describe the line appropriately and pick one point per section and refer to it. Good so far? A good analysis and reference should take time. Also, you should give scientific explanation why this is the case. Why is this, for example, if I'm talking a graph that looks like this, why is the earlier part here goes up so quickly? What is a scientific logic or cause for that? You say that. And here, why is it slowing down? Why is this leveling off? You need to give clear and detailed explanation if you want a 7 and 8. This is what makes a difference between an 8 from a 7 and the 6 from a 7. Okay? This here is this section here, the analysis section is for most scientists, including university papers, one of the most important sections. So make sure you talk a lot and give a lot of reasons. Now here, step 3, this part 3 here. Evaluate the validity of a hypothesis based on the outcome of a scientific investigation. So in this case, compare the trend with the hypothesis, see whether it fits. If it's the same, if your hypothesis and your data fits, then you just restate what's going on. There you go. If it's not, you need to give reasons why. For this particular summative, I'm probably going to give you a hypothesis. And then you will, based on the result that you collect, from a video or from something, see, hey, does this fit the hypotheses that that Mr. Chang gave me? If so, why? If it's not, why not? Also here, provide a concise 2 or 3 lines conclusion with a brief reference to the trend. You need to have an official conclusion. To do that, just write 2 or 3 lines. Make sure you refer to the trend line. Okay? Questions. No? Okay. This one, evaluate the validity of a method based on the outcome of the scientific investigation. So you need to make an appraisal. Appraisal, just a reminder, talking about strength and limitation. The range of independent variable. Now, someone from the other class was asking me this. Is range of IV, independent variable, the same thing as range of data? And they're not the same. Range of data here is essentially how spread out are your numbers in each trials. That's your range of data in some ways. So if your range of data is really spread out, that's something you must say is a weird or weakness. But in terms of range of your independent variable, this is your independent variable. Right now, this range of independent variables is only going from 0.2 to 1.0. It doesn't go, you don't talk about the really concentrated acid, like 12 molar. So it doesn't talk about that. So you need to talk about your range of independent variables sometimes, because sometimes your range of independent variable, you might end up having something like, for temperature, I'm going to mix something up, 5 degrees, 10 degrees, and then all of a sudden 23, 48, 60 degrees. So in this case, this is very widespread. It's not in regular interval. You talk about those things. Strength and limitation. Okay, strength, it's really spread out. Limitation is not regular interval. Who designed this? Okay, questions?
So it needs to be regular interval.
Ideally, yes. Yes, Jun-sang?
If we create the lab with criterion B, are we doing the lab on
No.
criterion C?
Nope. Now here, what else? You also need to talk about whether control variables are properly controlled or not. For this criteria C, I'll show you pictures, like last time, pictures of the setups and brief description how the experiment was done, but enough for you to talk about what are some design flaws. Now please, hi guys, look over here. Please, when you're talking about control variables and stuff like that, or evaluation, make sure you talk about the real systematic error that you see. Please do not say, please do not speculate things. Speculate things means you don't really see evidence of it, but you're guessing. You're guessing. Okay? So if you see on the picture, hey, it's like, wait a minute, this is not done, there's a problem with this design, then you talk about those things and how you fix it. Don't speculate. When I'm going over the heat of neutralization lab later on, I will go over with you. Okay? You see it. Here, this number lists the systematic and limitation in the methodology. I put a question mark, 3. You should ideally have at least 3. If the problem that I give you have more than 3, you better list as many of them as possible. Okay? Again, no human error.
But yes, random.
What?
What about the random?
What is your definition of random error? Something that's out of your control, but it's not human error? I will put it as a systematic error and limitation. But make sure it's not like random error, like Junsung somehow bump into you. It's out of my control. Okay? As far as I know, you guys are both humans, and those will be human errors. Good so far? Now, last bit. Explain improvement or extension to the method that can benefit the scientific investigation. Realistic improvement or extensions. So you need to say them. Now, this section here, like in this section here, what I would want you guys to do is that I want you guys to give me paragraphs, individual paragraphs. So every limitation will be one paragraph. So what I want you to see is something like, for limitation A, you say what it is, how it affects results, improvements together. Okay? Limitation B, the second one.
As a paragraph?
As a different paragraph, separate paragraph. Because one thing, when I'm marking all of the write-ups and I'm trying to do it quickly, if you put it all in one big paragraph, and I'm supposed to look for it, I might miss things. And actually next year, this is what we want too, separate paragraphs. So separate paragraph, one for each. I can easily find the improvement for A. I don't need to look for it later on. Okay? So separate paragraphs, please. Questions? Okay. Again, this document is on the website. You can look for it. Now, we're gonna talk about the heat neutralization reaction. Remember, we did the heat neutralization reaction using the styrofoam cup and the thermometer. What are some design flaws you see in here when I'm having this styrofoam cup like this and having the thermometer in here? What are some design flaws? Yes.
Your chance of
Tipping over. But how does that affect your result? You said there's a chance. And this is where, coming back, this is where I would almost grade it as a speculation. This is where it's like, oh, there's a chance there's a tip over. Is it tipping over? You might want to say it as a potential safety thing. You might want to say it as safety, but no, I wouldn't call it a design flaw. Okay? Yes?
Since you're holding the cup with your hand, the temperature of your hand rises to the temperature of the object.
Okay, good. So, whoa, that's actually a good one. So, thermometer, hand, 5 fingers. Okay, your hand. Don't laugh. So, in this case, since you're holding the cup, the temperature from your body heat from your hand might affect the result. It's a red cap, but it's a black pen.
But styrofoam has low heat conduction.
Styrofoam have low heat conduction, but still. And also another thing. When you're holding the cup, when you're doing the experiment that day, do you feel that the temperature was increased? Do you feel warm from holding that cup?
Yes.
Yeah, most of you have, especially the person who's holding the cup.
We didn't hold it.
Oh, you guys were just okay. You guys didn't hold that section. Okay, that's actually might be a good idea. So some people now, no, that's actually a good thing too. So some of you might not be holding it like this, where you might have influenced the temperature. Some of you might be holding only the tip, so you're not influencing the liquid, then yeah, you can potentially solve that problem. Very simple. But another thing is this. Some of you holding the cup and feel it's like, oh, my hand is feeling the warmth. If your hand is feeling the warmth, what does that mean?
Oh,
Yes, Jun-san.
It means it's taking heat from the cup.
Is taking heat from the cup. So yes, despite of the fact that styrofoam cup is an insulator, some of the heat was escaping through that layer of styrofoam and you detect it onto your hand. Okay, so there are heat escaping. What else? Where else is a heat escaping?
To the
Yes,
room.
oh wait, yep, Tommy? What? Well, you do want the heat to get to the thermometer, but yes,
I was going to say the
thermometer. Where else is a heat escaping, guys?
surface.
Yes,
Air.
Chris? Air, thank you. To the top. Okay, it's a wide opening. Okay, the heat is escaping out like this. So, now, just from this, there's like 3 different flaws already. So for this one, for the hand one, aside from for the hand one, maybe you want to hold only the top part of the cup, the top part. So you can hold only the top part of the cup. What else can you do? There are many possibilities of fixing this, or about the heat transfer from the hand. What else can you do?
Put it on the desk.
Yeah, but if you put it on the desk, remember it might tip over?
Well, you
Yes,
hold
just
it.
hold on. Yes.
It's like hold it.
So you can use beaker tongs. Beaker tongs. You could use beaker tongs. Now, guys, I don't want you to just copy this thing down right now because you probably will not see the same experiment on your criteria C. I want you to think, not memorize. So, what? Maybe you can use a cup holder. Okay, maybe you can use a cup holder like Starbucks. Okay, so that solves the problem about your hand, the heat from your hand. How about the problem about the heat escaping from the side of the styrofoam cup?
You can put the cover on the top of the styrofoam.
Okay, so you can have a lid on to solve the top part. So you use a different color. So that's to fix. That's a realistic improvement in terms of the hand warming thing. So you could, for a realistic improvement for this, you could say you can use a lid. What else can you do? Yes?
Like use a different cup that's like made out of more stronger like insulator material.
This is where, good thing that this is where give realistic improvement and extension. Now, when you give realistic improvement, I want you to be actually very specific in saying what you can do. So when you say, oh, use a cup that has much more higher thing. For now, it's a little vague to me. So can you give can you give a better example?
Using rubber.
Why would rubber help?
Oh,
Is rubber a known heat insulator?
yep. Isn't
Electrical insulator, that's for sure. I don't know about heat. Is it? Not that I know of. I haven't seen like any rubber oven mitts
what
yet.
about the materials in like
Styrofoam is a good.
Styrofoam is a good insulating material.
but then there's like
So if 1 cup is not enough, what should you do?
More
several
cups.
cups.
You do 2 cups. Oh, 2 cups. So you have 2 rolls of insulation. So you could, it's like, oh, for this problem, 2 cups.
Well, so creative.
It is simple and solves the problem, right? We're not looking for you to go to DT, design a solution, and come back with a beautiful machine and 3D print and stuff. I want you to give a realistic improvement that I can go to the back room, grab whatever it is, and bring it and solve the problem. Okay? Now, so have a lid, or if you can't find another lid, just take a second cup. Take a second styrofoam cup, break off the top part here so it fits inside here. And then you just use a pencil and break a hole.
Whoa.
Realistic improvement, guys. Simple, realistic improvements.
Does the DP expect like realistic?
Yes. Yes. The stuff that I'm asking you to do right now is pretty much what I'm asking my DP students to do. Okay? And pretty much, hi guys, pretty much all the DP science teachers are expecting the students to do. Okay? There are other design flaws. For example, when you're using the plastic tray with the... Now, some of you were using the plastic weight boat. I'm going to grab this plastic weight boat. Now, some of your plastic weight boat, I guess, because of the sodium hydroxide react to the air, so it sticks onto it. A lot of you guys end up using, just end up using your thermometer to try to scrape it off. Really, does it work well? No. So what should you use?
A different.
Just go to the back room and get another spatula. Get another one of those spoons, and then we'll scrape it off. You don't need to design anything. You just go to the back room and get some. It's a simple, realistic improvement, guys. Good? Okay? So this is what we want for evaluation section. Please, don't say something about, I will go and design a machine and build a machine that will give precisely whatever. Okay? If that is the case, I want to see the blueprint of that machine and the design of that. And I personally don't think it will be realistic improvements in terms of simple, realistic improvement for what you need to do. Okay? Yes? Chris?
Oh, but if you like scrub up with thermometer, I think it can like affect the measurements of temperature.
Yeah, it will. That's two. So that's another flaw in the design. Okay? So, but please remember, each limitation, hi guys, limitation need to have a separate paragraph, and you need to make sure you say how is it affecting the results, and then the improvement go with that particular paragraph. Okay? So that I can see it quickly and easily and clearly. Any questions? Okay? So all this document that I'm showing you in terms of this Google Docs, my lab guide that is still being updated, it's all on the class website. I'm going to take pictures of this page. And this video will also go on the websites under today's lesson. Any questions? Okay. So, please tell me that I actually pressed record. It's not one time I didn't press record, and that was annoying.